A hierarchy indicates we have an up-down. There's something above, there's something below. Inheritance is one example. There's other ones. In Java, the ones that we'll talk about in addition to inheritance for hierarchies is abstract classes as well as interfaces. So some parts I'll go through quickly, the theory part, because you have seen classes, not only seen classes, but a little bit of the theory of inheritance in 231, and you saw an example of inheritance, a very simple one, with exceptions. The idea is we have a base, and then we have derived ones. Derived ones, as the name implies, has all the characteristics, the information of the base entity, as well as its possible actions. A martial artist is a person, so that martial artist, she also has age, height, weight attributes, requires eat and sleeping, but also has some additional actions here. Review of relationships, because a hierarchical relationship is also a relationship. The hazard relation is a common one. I count that as, well, okay. Aggregation is the one hazard relationship for sure. A car has an engine, a lecture has students. One way where we have the hazard relationship is when we have an attribute of one class as a class is an attribute of another class. This is review. However, a new type of association is a relationship, is something. That's inheritance. These ones aren't top down at all. The car and the engine, one isn't above the other. It's sideways. We can send messages one way. With the ISA, that's where we do have a hierarchy, up, down. A car is a vehicle. An SUV is a vehicle, a more specific type of vehicle, a vehicle with certain characteristics. And depending on who you talk to, different people have a different image of what an SUV is. I think of an SUV as a certain, at the very least, good handling in rough road conditions. That isn't necessarily the case. In some cases, SUVs aren't any better than other cars, but that's my image of it. Apparently, I guess the general definition is height. Some of the SUVs, in my opinion, aren't SUVs. They just look like cars, but apparently they're taller. But nonetheless, say some SUVs have adverse road conditions. One of them I had, you could pull a lever and it would send drive power to all four wheels. That way, if some wheels were spinning. Well, it has that capabilities that cars typically don't have, and it has the typical car capabilities. Sports cars have the extra ability to, among other things, accelerating very quickly in varying degrees. Sports cars have better handling when you're going around corners, not under adverse road conditions like SUVs. So the hierarchy relationship is the sports car, if we were trying to conceptually, is a car. So it's below this one. Now, with OO trying to find the candidate classes, I've introduced already the classic approach where you try and find nouns in the requirements document. But, actually back here, the requirements document, I gave a hint of inheritance here because I had classifications. All these are forms of animals. All these are forms of staff, more specific forms of staff. And we could have more than, actually, we have more than just administrative staff and animal care staff. We could have managerial staff. We could have kitchen staff as well, too. That's where inheritance comes into play. With inheritance, if you have classes, say we've got some animals in our zoo, they have common behaviors. Under the current approach, what you've been taught so far, specifically in, well, no, actually I had to jump ahead. Assuming I didn't jump ahead in exceptions and show you how a simple example of inheritance, prior to that example, you would have to define these behaviors, methods, in every class, animal class, which is terrible because it's waste. We make our program bigger than it has to be. It bloats the size of the program, in other words. It's harder to maintain because as we go through version to version with version control and Git, you should be making local versions. Then it's the same behavior, then we have to update it again and again if it's the same behavior. So this is where inheritance comes into play. When we're in the design phase, not in the implementation phase, what you shouldn't do is implement it this way already and actually write the code like this. What you should do is be designing the program before you write a line of code. What classes should exist? Now, the assignment is prescriptive, extremely prescriptive, where it specifies exactly what you have to do, which isn't a bad thing. I tend to do that, at least in the first assignments, because people need the guidance. Later on, at least in 233, myself, when I write up the specs, I have at least one assignment when possible where they have to come up with things. So coming up with things, you should be designing, thinking about theoretically what classes exist, what behaviors, rather than writing this as code. So you should be thinking, what's the common behaviors that we have? If you came up with those different animals, well, there's things common among the animals. Then you can define a new class that includes all the other ones, that includes all the other common information and behaviors. And now what we have is when we're designing this, is we're not changing code, but then what we previously had in our earlier design, that drawing, or we put it out in text, we put here. So this is why you should be designing before you write your first line of code. So it's easier for me to, oh, okay, conceptually I move it here, as opposed to me trying to cut and paste the code here, which is going to cause many, many problems, syntax, logic, maybe runtime errors. Okay, terminology. There's many ways that are in common use terms with OO. This is the parent class. These are the child classes. That's where we have the hierarchy above and below. The parent is above the child because the parent is used to derive the children. The children all have the capabilities of the parent. Now, with the public part of it, yes, of course, anybody can call these methods, but with these child classes, you can directly call them within these methods as if it was defined here. So this UML class diagram is a nice synopsis saying, we define eat here, but we don't define eat here. But I can call eat from another method as if it was defined if this was down here. And the UML representation is we have this type of arrow saying that, and it's slightly different from the other ones. It's actually a triangular one, not the diamond with the association and so on. And it's not just the arrowhead with the association, but it's the triangle saying that there's the inheritance relation. How high up should you should define information high up. You should define methods high up. How high up? As high up as possible so that this behavior applies to all the children. And that's an efficiency issue. If you put it too far down, if you put it here, then you also have to put it here. If you move this from here to here, then we also have to have that behavior. So it should instead be here, so it applies to both. Of course, you shouldn't apply higher, define these ones higher than they should be, because then we can have, if we define it too high, we have, say, another class here, all the entities, all the objects on the earth, living and non-living. We obviously could put this in all the entities, the non-living, because non-living entities don't biologically do this. And then we have the ridiculous case, if we have the behaviors too far up, like fly, all animals fly, then you have pigs fly, which isn't a good idea. Now, public attributes and methods can be directly accessed as if they were defined here. Slightly different from other classes. Other classes, when they call the methods, they can't directly call them. They have to instantiate an instance. We don't have to instantiate an instance here. What about private attributes? Well, the private ones, you can't directly access in child. Private means you can only access in the class, but you can access the information through accessor mutators. You inherit those ones if they're public. Syntax, fast here. Just use the keyword. That's the parent, that's the child. And if you read it, it makes sense because the lion has all the capabilities of the animal and more. So lion extends the animal. Very easy. And then we add new methods that are unique to this child class. Roar, lion roars, but animals don't roar in general. First inheritance example, simple one, just to show you code. It's a little bit more than the other one I had with the exceptions. So we have class person. Keeping it simple, we have at least one attribute so that we have a real class. constructors handle different cases, but the one of interest is right here. Do person stuff, simple text messages, just to encapsulate or show these are some common behaviors of people. When you see it, you will know that we're calling class persons do person stuff. Eat, sleep, and you see the messages is what people do as long as they're alive. Well, maybe not the fruitful thing, but that's an option. Hero is a person as well, but by the extent, it means a hero is a person and a whole lot more. And I picked these names for a reason. Over here, before we get to the next one, this does fulfill syntax requirements. But aside from having learning, for learning purposes, you wouldn't normally do this. I've done this for learning purposes because I just wanted to draw attention to your fact. Here's how we actually create a child class. That's a syntax requirement. Why would we do this in real life aside from learning? Outside of learning, why wouldn't we do this? Any thoughts? Well, what's the point of doing this? If we have a class that's completely empty, it's like defining a method with no body. I just did it for learning so that I could focus on this. However, you're not required by the syntax to define new attributes and methods, but you really should, because that's the point of having a class, unless you're writing some test learning class to help you learn. So I put in blue here, what's the information and the methods that are unique to the child. We have hero count. Well, hey, if this buddy is a hero, he has to do heroic things. And the hero count is when the person does heroic things, calling this method, then we count it. We start off with 0 heroic things, and then when we do something, we increase the count. And a person is not a hero, so a person doesn't have heroic count, nor should they. I pick these, so it makes some conceptual sense outside of code. So it's the driver running this. We have Clark, that's a regular person. We have Superman, that's a hero here. We have Clark. We call the do person stuff. The messages give you an idea as well as the coding. Which method are we calling? We're calling the person's method. These are common behaviors for a person. Now down here, we call Superman's do person stuff. There's no do person stuff defined, but because Superman is a hero and a hero is a person, we have access to this automatically. So the eat, sleep, so on appears with Superman. Benefit of employing inheritance. Inheritance is one example, but not the only one, of code reuse. You write the code once, test and debug it reasonably well, and then you can reuse it many times. Think about class scanner, class string. Those ones were written by the staff at Sun and then Oracle after they took them over, and it's used umpteen times, so you don't have to write the code yourself. So we can have other child classes. We write it once, and then we can use it thereafter. If there's problems, we need to debug it or add new features. We do it here, and it's automatically available here when we instantiate these classes. Beauty. Overriding. When I talk about overloading, I looked at the ceiling, not because I was rolling my eyes saying, oh gosh. I was trying to be careful because these terms are similar in spelling, pronunciation somewhat. So I was trying to avoid doing a slip of the tongue, transposing them. So I did it again, very carefully, overriding. Overriding, we have an existing method, but the overriding means we use this method instead of this method. Or wording it different, overriding occurs when the parent and child both have their own version of the same method. The code's different. Overloading, which sounds kind of similar, difference. Overriding, it exists here, and it exists here in the parent-child. Overloading, they are different versions of the same method in the same class. And what distinguishes these methods is the parameters, the type, number, and order. Those are the ways that a compiler can determine the difference between different versions of the method. But stylistically, never distinguish, have two different versions of the same method where the only difference is the order. Don't have an int string and a string int. Compiler can tell the difference because it's precise, but it's easy for a programmer to make a mistake and call the wrong one. And presumably each one does different things. Overriding example. So the rest of it's the same, so I abstract it. No need to add clutter. We have a new method over here. Do person stuff. Let's go back to class person. Class person's do person stuff was basically just describing general biological needs characteristics. We've got now version 2 of class hero that's the snooty one. Sleep? No, I don't need to. Poof. I just got that from a Superman when Lois Lane was interviewed. She tried to say that nicely. Do you secrete? But then she said, do you eat? Funny how things like this, that was the old one I remember as an example. But it stands out here so you can tell the difference between the heroes version and no, Superman wasn't a snob. He actually was nice, very humble guy, versus the regular one that lists biological characteristics. So when you run it, you can see the difference. Okay, now this is version 2. The driver class, we have a person and a hero. With the person, we didn't change do person stuff, so we have the same message. But I have this copy paste message. This is the person's do person stuff. Now, because we overridden it, we don't call the persons. We have the snooty message. A contrast. Yes, indeed, it's different from the persons. Because Superman is a hero and not a person, and we've overridden this, we call this the hero's version and not the person's version in this case. Checking for overridden methods. This is something I didn't use before this, so I was actually learning it. It's nothing too complex. Learning it this semester. It's kind of handy. It enforces in syntax. It uses the compiler to reduce the chances of you doing something really dumb. That's one benefit of this. When you're doing overriding, see, I'm thinking, making sure I get the right term. Also, it flags potentially to other programmers that this method that you're writing in the class is a child of another one, but has this method, we're overriding default behavior. Because otherwise, if you don't document it, the person could be expecting this behavior when we get this. So documentation explains that we overrode it. Another benefit, however, besides acting is documentation, because what you might see is people, some examples, they do this. So it might confuse you. In that case, it just looks like the override annotation is documentation. But I said it also helps in the syntax. It adds it checks syntax for you. So if we use the override annotation, but we don't treat it as documentation, here. I do right here and do right here. And I didn't bother with constructor because we can't override the name constructor per se. So when I compile this one, it checks to see do person stuff. Did I override it? Yes, indeed, I did. In this example, I added the override here, or in a later version based on this. So no problem. But it checks to see if I add the override to something do hero stuff, that only applies to hero. It wasn't in class person. It then gives me this error message. It doesn't override it. Now, with overriding, who are you going to call, as it were? Which version of the overridden method do we call? Simple part of it, I'll explain how it can be determined by the Java virtual machine, Java, the interpreter. And then I'll talk about, this is one of this overriding who gets called is actually one of the beautiful things of OO. OO has strings, procedural has strings. So I'm doing my darnest to show you strength. This is one of them. I won't have time and say, because I didn't do it like this morning's lecture to show you the beauty, but I will show the mechanics. Binding, we have many terms that are necessary to go through. They're actual terms. Because these terms are in actual practice, but they're very precise and it tells us what we're referring to. When we have a reference, that's a specific term, and a method, that's another term. How do we know which method's called? Well, that's where binding comes into play. It binds the reference with the method. If we don't have overloading or overriding, easy. It's unambiguous. If this is class person, the whole definition, we have Jim and set age. Well, there's no ambiguity whose method we called. That's the only one. It's not an overridden one. But if I've got multiple versions of a method, either in the same class that's overloading or in the parent class that's overriding, now we've got more complex binding. This you have seen, but the terminology. Early binding applies with overloading. It's determined at compile time, and this is how it's determined. If you think about this with overloading, if say we call a method, and that method, we call it and we pass parameters that aren't in any of the method definitions, it'll say you're trying to pass this, say we try and pass in a boolean. And there's no such method. It'll say there's a mismatch between the method call here, a boolean, and the class definition. And it does this, it's a compilation error. Whether you're calling one of your own methods or you're calling a pre-created one. This is referred to as early binding because we have a process of translating and running a program. Early on, we have to compile, translate before we can run it. Late binding, on the other hand, you see with Java now that there's a distinction between translation and execution. It was hard to see when you have Python because it translated, executed a line at a time. And it didn't produce by default an executable file. Time, okay. Late binding, on the other hand, later in the process after compiling, if there's no syntax errors, then we run the program. When we run the program, if we have different versions of the method, that's later in the process. How do we determine that? This applies when we override. Overloading is early binding. It's determined by the parameter list when we compile. If there's a mismatch between the call and the definition, doesn't compile. If we then use overriding, there's a method in the parent and child. How do we determine? Do we call the parents or the childs? That's determined at runtime by whatever reference we're binding to that method. If the reference, in other words, points to the parent, we call the parents. If the reference is a child, then we call the childs. And this is hinting at the beauty of this. Well, I'll get to, it'll be a cliffhanger over the weekend. Reminder here, so you don't mix these up. Overloading, same class, different method signatures, different parameter lists. It's what's in the round brackets or the absence of anything that determines which versions of these methods we call. And various examples. No parameter calls this one. Integer calls this one. Character calls this one. If we try and pass a string to display, there ain't no version of a string. They'll say there's a mismatch between these two in compilerese language. And this occurs early on at compile time. Overriding. Again, the reminder, because this is a new term. Different versions in the parent and child. The method is the same in terms of the signature and the return value. So we don't distinguish which one parent-child gets called. The one that's determined, we determine this at runtime, and we'll see why the runtime, this is going to be the beauty of it. And that's determined by whatever type we have here. Is it a parent? Is it a child? Is it somewhere higher up the hierarchy? A parent of a parent. They don't have grandparent term, but parent of a parent. And the example that we had Clark, that's a person, Superman's a hero, because the type of the reference here is a person. We call persons do person stuff. This is what you saw implicitly, but I'm explicitly telling you how did we know that we're calling persons do person, because Clark is a person. But we have Superman, that's a hero, because the type of this reference, the implicit parameter, is a hero. We call it the hero's version. You saw the output, but I didn't give an explanation yet because it's doing a step at a time. Terminology. This term here leads into the beauty of late binding. Polymorphism. These are actual OO terms, so I am dumping a lot of terms on you, but they're commonly used terms, and they will help you throughout. This will help you understand the beauty of it. The next one, superset, subset, it's actually a keyword, super, and understand why. So we need these terms. Okay, polymorphism. Name comes about poly. A polygon is basically a the poly means multi. Polygon means multi-sided shape. Morphic means forms. Together, it means many forms. Polymorphism means that a method has many forms. It's a term for overridden methods. So example, we have method having do person stuff, 2 different forms. Okay, this term, it's an alternative term, super and subclass for parent and child. Again, why am I introducing it? One, because parent and child is used as frequently as super subclass. Another reason is super, that keyword, it's actually a keyword in Java and many other languages. Now I introduced the super and sub terms in terms of set theory, because most people use that keyword super, they get it backwards. Are we calling a parent or child? Set theory. We have 2 sets. This is a subset of this one contained here. Now, the keyword super means how many entities, whether they're physical or abstract or non-corporeal, belong to this group. This one's easy to see. This is referred to as a superset because more people belong to it. I think 6-8 billion right now, approximately equal to. The people in Canada, well, there are also people on the earth, but it's a subset. Fewer people belong to it. I know, 40 million-ish. Not drawn to scale here. Now, keep in mind, that's the superset, that's a subset. So what determines a super subset is not capabilities. That's where the people fall in the pitfall of code. Super means which classes belong to it. Super has more. So the parent is a superclass, the child is a subclass. Why? Think about this. You have a button. A button control in real life, these are basically buttons where you can press them. Or over here, it has that pressable behavior. But this type of button here allows you, it's multi-select. And it makes sense based on the question. However, buttons also include a more specific type of button called a radial button. A radial button, that term comes from the old car radials, where you had the analog ones, you had the dial, so you're actually picking up local radio stations, or you had these presets where you could record station number 1000, station number 1100, have these shortcuts rather than having to turn the dial. But if you press 1100, fine, it would play that station. Then you pressed another one, 1200, this one would pop up. Radio buttons, you can only select one at a time. That's an actual programming term. So the radial button, if we selected paper manual, and then we clicked over here, this one would be unchecked. So it has the ability, radial button, the ability of a button, but it has the more specific one where it checks to see when you click on something, is something else clicked. Now you don't have to know the radial button, but now I'm getting at this. A radial button is a button. And we also have other buttons as well besides these 2. Now this is the superclass. This is the part that you need to know here. The explanation will help you, the need to know part, is this one contains more classes. More classes are instances of a button than a radial button. This is like the population in Canada, population in the world, more people belong to it. This is like the population in Canada, fewer because it's more specific. That's where the super sub comes into play. If I use the super keyword, I'm referring to the parent because super, that terminology wise, that's the superclass. So That's an actual keyword, and I introduce it because it is commonly used, but also to help you understand which class's method I'm calling. Super means parent. When I was first learning this, I thought super means more capabilities, and that means superset would be this one because it has more capabilities. No, we're talking about how many belong to this one. In that case, this one is super. Okay, so back to this. Why do we need the super keyword? Well, suppose that we had, well, actually, let's go to the code here. Class, actually, let's go to the actual code here. We copied this over. Examples. We got 5-6 minutes left. Hierarchies, inheritance, overriding. So we have class hero, class person. We have the overridden method, do person stuff, that's defined here and overridden over here. But a question, they didn't ask in live class, this semester's kind of on the quiet side, but sometimes people ask, well, what if we're here? We have to have unique behavior, unique instructions, but we also have to take advantage of these instructions. How do we do that? That's where the super keyword comes into play, because by default, if we override a method, this one hides this one if we have a child class. Therein, folks, is the need for the super keyword. And you need to understand what super does. Super accesses the super class's capabilities. It could be an attribute if we have permissions to access it, if it's public, or it could be a method. So with the example, do person stuff, in the current version, with class hero, the previous version, we only get the hero's unique behavior. But what if we want the parents as well as the heroes? So we have this, then this is how we explicitly access the parents or persons do person stuff. So we run this. Should I? No, not quite yet, actually. I'll organize this. So we need super first when we have an overridden method, and we want to access the parents method as well too. Without super, we'll only access the child's. With unique methods, the hero, do hero stuff is unique to the hero. We don't need super because there is no such do hero stuff here. And there's no super, and someone asks, what if we have another one over here? Higher level, there's no super. It means we have to go a level at a time with one super. Now with this example over here, the learning objective is using that super keyword with an overridden method. So do person stuff, we'll see the message, the snooty message over here. And then there's a time delay. This time delay is implemented well, but I did it simply. There's a better way of doing this. If you want to know a better way, using Java threads and put class thread and putting it to sleep. But this is dead simple. We have a loop, empty body, so it runs, I don't know how high that counts to, billion trillion times, and there's a time delay depending on how fast your machine is. So a times delay between showing the snooty message and showing the person's message. Whether or not you detect it easily will depend upon the speed of your machine. My laptop, let me talk, give me a sec here. In class was fast enough that you could barely notice that delay. You see the first one, oh, and it's a fairly long delay before you see the second one. Even though this was a powerful gaming machine, now the processor used to be powerful. It's actually slower as a whole than my laptop. Okay, so that's one thing over here. I'm just trying to illustrate when we have the code in the overridden method, but we also need the Parents method. Second learning objective over here. Private. I said by default that your method should be public unless you have reason to make them private or something else. And I briefly said private methods are used for helper methods where essentially they're performing a task, a utility task, just for other methods of the same class. It generally doesn't make sense to have this time delay used by someone else in another class. So I make it private so it's not accessible here and it wouldn't show on the API. And as a helper method, it's just called by methods of class hero here. So the other bird that I'm hitting with this stone essentially is also helper methods, an example, and a concrete one. It performs some capability for the other methods. Over here with the super, I'm not gonna have time to go through this. We're slightly ahead of the other class now. We'll use it with the toString. toString, recall, you should write your own if you want to properly display the state of your objects. There is a default toString that's in part of class object. What you're doing is you're overriding it here. And this example will show apparently, I can't remember it off the top of my head, toString and overriding of super. Well, it is overriding, but also super keyword. So let's stop there. So we have class person with an age, and we have two constructors. One sets default, one sets parameter, the regular do person stuff. But what's new is toString method that displays the state of the person object with just that one attribute, as it should. Just its attribute, can't access a child's. The hero class, we have its own unique attribute and its own unique method. However, there's two constructors here. One takes no parameters, one takes an age parameter. In this case, we call super, just a super keyword, which calls the super class's constructor. Now, if you have the super without some access field, dot something, and you're not in the constructor, then the compiler is going to flag it down saying something effective, you're not in the constructor. But it sets that attribute that's specific to the person to the default value. This is specific to the person, so it uses person's capability. And the same with the case when we create a hero and we pass to it a starting age. Because age is part of the person, we use the person's constructor to take care of that task. However, with the heroic count, we start off with default to 0, and we do it in this constructor because it's specific to heroic count. That's what we've seen before. But we got the toString method. The toString method's illustrating a two-part toString method, seen toString before. But in this case, this toString is, well, we're leveraging the capability of the person class to display the state of the person object, whatever attributes are associated with the person object. Just one in this case, the age, but there undoubtedly could be more for real classes. Even though I'm writing both classes myself, in this case, don't assume. I check to see if it's not null, because if this is null, I'm trying to do a concatenation, it's going to have runtime error. It's going to concatenate the previous fields of class person with the specific information associated with class hero. So it's a two-parter, but it's delegating some of the tasks appropriately to the parent when we're looking at the parents. Oops. When we're displaying the state of the parent's attributes. Oh. And so we've got a person, calls the person constructor, age is set to 55. We've got a hero, age is set to 25. And that's age is set through the person's constructor, indirectly through the hero's constructor. Take advantage of pre-created code, whether it's your code or someone else's code. So considering you have the hierarchies, if the code is already or should be implemented in another class, then pass it, delegate it to that other parent class. And you do have inheritance that you need to plan the assignment. However, the task that is specific to this class hero, because heroic count is names hill could be a clue here. Heroic count is specific hero. We do it in class hero. We set that attribute. And with the toString, with this toString here, it's automatically called when we pass the reference at print ln. And let's see, toString class. Oh, this is class person, so it just person's toString method. Here, the Superman one. We call the hero's toString method and immediately calls the person's toString, which displays the state, whatever information is associated with class person, and then it returns that state, and then pops it up, if you will, with the state of the attributes that are specific to the child class, class hero. So it delegates the behavior. Any questions about this? This example is not a new one, but pulls together some concepts and such as toString and super all together. Now, there is a method that is actually behaving in a similar fashion to toString in Python. It's so useful. We didn't have it wasn't the curriculum. I didn't have a heck of a lot to cover it myself. The other guys might have covered it. Do you know what method that would be? Anybody? And hint, it's not called toString in Python, but it behaves in the same way, essentially. What's this? str. When you get some time, you can try implementing this. Remember how to code in Python now. Implement a class and the underscore self. When you pass a reference to an instance of a class, it automatically calls that str method in a similar fashion in this. And whatever code that you have here, well, you should return a string representation of the state of that class. There's the other one, I believe this is spelling of it, that behaves similar to the equals, the Java equals. Just mentioned it exists. Okay, so synopsis of this example, super will in itself accesses the parent class's constructor. So consequently, just super should be in the parent, the call to it should be in the constructor, not something else. There will be a syntax error. Here we are using super keyword to access the parent class's capability, in this case, toString, but it can also access, given the permissions is allowed to the child, the other attributes and methods of the parent. So you're delegating the learning objective on top of this is you're delegating behavior that's appropriate to the parent class. Don't have it done in child class, even if the child can access it. And then the child class basically implements the behavior that's specific to a child. So you have to think about design. What behavior, in other words, what methods is appropriate to which class, the parent or the child? And ideally, going back to earlier, try and put that behavior and those attributes as high in the hierarchy as it makes sense, but no higher, of course. He's pretty specific in assignment 2 again, which is not a bad thing because it's your first, not only your first object-oriented assignment, but it's also your first assignment implementing hierarchies. So handholding you through it with a certain design is not a bad thing. It gives you some structure. I don't remember I've gone through enough to see if it actually allows for some freeform, but eventually you will have to do this freeform and design yourself. So there's 3 levels of access now we talked about officially, and here's the UML representation. See this? And the new level of access is the number sign for protected. Now, protected means that if you have a variable attribute that's protected, it's also directly accessible in the child class, which increases the coupling. Consequently, you should be really hesitant to use the protected level of access, because if you have an attribute that's not private, now you open up the child, potentially anybody that extends the class can access it directly and muck it up. The way you prevent a class from having child classes, making the class final class. Talk about that in a bit. So generally, this should be private for variable attributes. On the other hand, methods, unless you have good reason, it's a helper method, it should be public. So that functionality, because it's instructions that do a task. The protected that closes it off. It's not necessarily a inappropriate thing, but it should be done with caution or done sparingly. These are by overwhelming of the 2 permission levels that you should use. Protected only if it makes sense to provide access to the parent and its children. So we have this table here that summarizes it. Public, as before, it's still available. anywhere, except I'm more specific, I have class and subclass. But basically it's anywhere in the program. Private, only accessible in the class in which the private attribute or method is defined. Same as before, nowhere else. The protected, same class, of course, not a subclass. No. So the gray indicates where it's accessible. And protected means it's accessible in the subclass. Normally what I do when I'm doing my own schedule is I actually teach OO early on, then I teach hierarchies, and then get this gelling in your head through an assignment so it's clear in your head. But we flip the order with this semester where packages are talked about. And so packages, it's kind of a little bit wonky. We introduced that fourth level before actually introducing this level. Now, someone might call me on this and say, wait a minute, because they fiddle around their code, and I'm aware of this, so it's not really calling me, where they say, I have a protected method or attribute, doesn't really matter, something that's protected, and they say, I've got class X, class Y. Class X has something that's protected. Class Y is not a child of X, yet I can access it. Your chart is wrong. This is under normal circumstances. It doesn't introduce that fourth level of provision, package, essentially, which you get to. I wanted this to gel before you got the packages, but c'est la vie. The package level access, recall, is set when we don't specify an access level. And you specify package at the top of the class definition if you specify one with the keyword package and then package name, whatever it might be. And you probably want to give it a better name than that. If you don't specify package, then that class X is still in a package, the default unnamed package, which essentially is all the classes that are in the same directory. So anything that's package level access for attributes and methods for now is accessible, not only this class, of course, but other classes in the same package. And if you have no package name, then that means that, that means that class X is now part of the package. If I have no, I think there's a method, and I have a X. Because I has package level access, I can directly do this. That's what the package level access means. And you can do it with methods as well too. Now, putting it all together, well, you had a few minutes to have this gel in your head to protect it. So public is accessible anywhere again, whether it's another class in the same package or subclass. Private, only in the same class. Those are easy to answer. Is it accessible? Now the protected, someone who might call me on it, they quite rightfully say, well, I have something that's protected. Okay, it's accessible in a subclass, but I can also access it in another class if that class is in the same package. If that class, if we have one class and something has protected access, say this one is package pack. And this one is in a package pack 2. Then this is a syntax error. Two different packages. Oh, sorry. If we make it protected, not package level. Well, actually package level as well too, because they're not in the same package, so we can't access I. If this is protected, it's not accessible. On the other hand, if we get rid of these two, and they're in the same, or if they're in the same package explicitly, then this is no longer a syntax error. So if something is protected level access, as I just demonstrated, you can access it in other classes. Sorry, if something is packaged, you can access it in the same package. But the protected, generally, you can only access it in the same class or subclasses, or now we introduce squeeze in package classes that aren't subclasses in the same package. For example, class X, class Y. We have something protected in X. Y doesn't inherit, extend class X, but if they're in the same package, X can access that protected whatever method attribute. And you should have this handy. It's something that a programmer should know for sure. This and this, because these two are the ones that are going to be used overwhelmingly. These only if you have a good reason, but I suppose it might show up on a quiz. And also, on top of that, in the future, when you really start making real programs, these ones start showing up more when you actually set the access level of this to protected package. And this is just a code example, make it a little bit more concrete. We'll do it fairly quickly. So we have class P, we have 3 levels of access here. Of course, we can access everything. The child, private, we cannot access. We can access protected because it's a child, and we can access public, of course. Driver depends here. We can, of course, access num3, public, always. We can't access num1. Well, that's a given. You've seen this already outside the class. Protected, generally you can't access it unless driver's in the same package as P. So what permission levels to set? A recap of what I said. Rules of thumb though. Variable attributes private unless you have good reason. Methods public to provide that capability. And if you have helper methods that are specific to the parent-child, then that's a justification for making it protected. Scoping rules. Now that we've got 3 levels of access. Scoping rules. PowerPoint's a little funny. That's here. I get on full screen mode, it goes over here to where I started. Yet this morning, it's where I ended full screen mode. So I have to keep a really close eye on it. Okay, scoping rules. You have to have seen scoping rules after we talked about functions in 231, where you can access something. Scoping rules, once you start talking about functions, you have an identifier. Print some identifier name, a constant or a variable. You look for that name. Has it been defined in that function? You look locally. If it hasn't been defined, then we look globally. We don't have real globals in Java, but now the next level is look for a definition. We look locals first, and then the class definition. That means that, as you've seen, I had a mutator like this when I talked about this reference. If we have a local that matches the name of the attribute, it shadows or hides it. Because we look here before here. If that identifier is neither place, then we look at the parent class. We keep going up the hierarchy, parent to parent to parent, until we hit class object. If something's found, then it's a syntax error. Identifier is unknown. So this is scoping rules. If we refer to an identifier, we look here first. If there's nothing here, and only if there's nothing here, do we look here. And as I say, the shadowing means something shadows or hides something else at a different level. We have local variables that shadows or hides global variables in Python. Local variables here, we have like this here, then that num. Then this num shadows or hides this one, unless we explicitly access this one, as we'll see. Now, if we refer to a num here, don't have it here and here, then we look in the parent all the way up the pipe to object. Now, as you've seen with this should be a review, but I'm putting it together with super. If we have a local and we have an attribute, the 2 names match. When I first talked about this and I had a mutator, if you had an attribute called age and the parameter is called age, then how do we access parameter? With this reference. This dot age would basically access the attribute. just age itself, if there's a local or parameter, would access the local. If you actually want to access superclass when we're here, then we, as we saw, preface it with super. If basically it's shadowed at this level or this level, then we can explicitly reach the superclasses here. We can't do super, we have to go one level at a time. And this isn't uncommon where people have these logic errors where they're accessing the wrong variable. One instance where people do that is with mutators. And I should mention, some of you have been actually starting to encounter these, what should we call it? Null pointer exceptions. One possibility of null pointer exception is if I have some attribute it's S. And then I have a mutator method, and I want to set S to this value. A logic error the reminder is this. You can be staring at your code and going, dang, this I set it to the value of that string. Yes, you set it. What did you set? This contains the address of a string. Reference to identifier, we look locally. We have a local S here. So we take that address stored in the parameter. Where do we put it? Well, we have reference S again, local. We put it in the local S. Now, all this does is set the local S. This attribute S is null. And then later on, when you try and access the attribute S, it's still null, no pointer exception. In these cases, trying to figure out where the error is, well, you can have an assertion, check the post condition. Post condition, the attribute S should not be null. Or you can use things like the debugging statements that I talked about, where essentially you can, if you're really clued out why it's null, essentially have these output statements and try and backtrack in your program to, if it crashes here, then have prints to try and backtrack to figure out where it actually was null, or was it null all the way through. And finally, you can use debugger to try and look at the contents of that attribute S. Now, I have had people contact me about a null pointer. Not sure if it's this. They never actually did. They said they figured out the error, but they never actually said what the error was. But it was a null pointer. What caused it, I don't know, because they didn't get back to me. And I couldn't run the program because it was incomplete, so I couldn't try it. I could only make suggestions. But I would have tried various things like backtracking, assertions, and so on. So forgetting this stuff, it does happen. I've done it a few times myself as a student. Sometimes I might do this goofy thing myself as a prof. An extra little illustration and notes, just in case, because it occurred to me as I was going through this that you might not really understand the abstract. Hoping you would. No one's ever complained in the past, but doesn't hurt to have the extra. So we have the default versus accessing the parent. In the parent, we have a method 1. Child, we have a method 2. Same method. How do we determine which one we're calling? Well, if we don't have the keyword super by default, scoping rules, we look in the current class for that attribute or method. So that's the default. If we want to explicitly access something in the parent, the super is the superclasses attribute or method, so we have access permission, and then we access that version's a method 1. So essentially, if we have an overridden method, the child's hides the parents unless we use the super keyword, as it should, because we're actually writing a different method here that's supposed to have different capabilities than this one. Here we have the default. We're talking about an attribute. So what we have here is we have an attribute age, but we also have a local. Scoping rules, if we access that identifier, in this case it's a variable, could be a constant, and we don't preference anything, the default is we access a local. The locals basically hide or shadow the attributes. That's the term. We look at local shadowing attributes. If we want to specifically access the attribute that has the same name as a local, that's where that this comes in. And that's one of the reasons why that this exists for every class method. In Python, they cram it down your throat and you have that self passed in here. Guido made a design decision, make it explicit. Whereas the this in other languages, C++ and Java, is implicit. Either way, it's accessible. If we have the self here, we can say self.age to access the attribute. Or if we don't explicitly have to pass it, that keyword this is built into syntax, Java and C++, and that means access the attribute and don't access the local. Just local. Okay, casting. Casting is you're converting from one type to another. Unlike Python, you have an operator that can theoretically convert from any type to another. Python does not have casting. It has functions that convert. It's different because there's limited functions where you convert, takes one type, takes a string, returns an integer. That's all that function does. Casting can theoretically, as long as it makes sense, convert to any type, any type. And you need to do the casting. What you should know is if you're going from something that contains more to something less, one memory address here. Real number, it's a bigger set than integers. So essentially we have to tell Java, I think it's the Java compiler at this stage. Yeah, it's checked at compilation time. Java compiler, how we're going to treat that. In this case, we truncate it. We convert that, we lop off the fractional portion because we're essentially telling us how to handle the fractional portion. Over here, and we could call round whatever mass rounding function, but in this case we're truncating it and we're just getting the integer volume. Because we have more, we have to tell the compiler how we want handled. On the other hand, if we go from less to more, you should know from your basic mathematics, the math number types, that an integer set is contained within the real number set. Real numbers contain integers and more. So we have less here because there's no fractional portion. You're trying to store it in a memory location, you can store more, no problem. A similar idea applies when we have objects. Now this I go through a little more quickly because I went through the objects quickly, where we had exceptions. With exceptions, recall that exception handling, you had to catch the child before we catch the parents. The bottom line here is, if you get more than you expect, that's fine. If you get less than you expect, that's a problem. And we'll see that when we talk about methods and calling methods when parent-child. Furthermore, if you try and misrepresent things with casting, you try and cast that, as it were, the equivalent of that $10 to $100. The outside of it looks like it's $100, but then when you actually try and use it, that $10, well, you're going to have problems, a runtime error. Now, an example of this inheritance hierarchy to illustrate this and finally get to when you say the beauty of polymorphism is here. This inheritance hierarchy is from one of my old 233 assignments. Now, when I illustrate the beauty of polymorphism, I use a dead simple example. It's just text messages to make it easy to see what's happening. But I also have this one just to twig in your mind that overriding polymorphism is extremely powerful. They don't have to be just simple text messages. Here in their assignment, I've had some cases where I separated first OO assignment from inheritance. Sometimes I actually have the OO assignment reused again with inheritance. So the OO assignment, no inheritance, no explicit inheritance, was they had a starship class and had instances that computer ones and human one that could attack each other. So they had an attack method. And it had I think it was a random amount of damage they do to each other's ships. But then in the object, the hierarchy, the inheritance version, then we could have more specific instances of starships. They had their own attack. So this one had more damage, superior, or this could attack in different ways. Some of the attack, for instance, could penetrate some of your defenses more quickly. It didn't do any more damage. Or some other special attack. It crippled part of your ship or something to that effect. Furthermore, in their assignment, they were required to implement some behaviors for the ships that were unique to this ship. Regenerate, they're peaceful, the Federation's peaceful. So their technology, unique technology, is the ship would regenerate damage. This one, on the other hand, the utter battle cry, the Klingons, is a Star Trek motif. Warrior race, very good fighters, and they sing before combat to bring up their morale and bring down the morale of the enemies. And that's unique to the Kling ship. Now, using this to illustrate some of the things, the beauty of polymorphism, get to this, is the Fed ship is a starship. A Kling ship is a starship. So if we want a starship, we want less $10, but we get $100, we get a Fed ship, that's possible. Because if we're treating it like a starship, that Fed ship, both of them have the attack method. And the same with the Kling ship. So we can go up, we can substitute up this for this. However, we can't substitute down. We can't substitute. A Fed ship is a starship, but a starship is not a Fed ship. That's where we have the hierarchies. Why can't we substitute this for, this for that? Why can't we go down? Thoughts? The diagram gives you a big clue. So we want this, $100, but we get this, $10. Intuitively, there's another hint. Intuitively, we want more, but we get less. What's the problem with that? Well, if we have a Fed ship, it doesn't have that regenerate method. So it's a problem. We call a non-existent method. We can try and cheat, and we try and cast this from a Fed ship to a starship. Then we think it's like that envelope. We think that it's a Fed ship. We think that it's $100, but then we open up. The equivalent to open up is calling that regenerate method. There's no method to call. That's why we can't substitute a parent for a child, because the child has more capabilities than the parent. And it illustrates when we try to access the non-existent capabilities. Now, the beauty of polymorphism or overridden methods. It's just awesome. Simple little example here without getting into the code of what these two different methods do. We have one type of starship, another. Let's see, starship has an attack, Kling ship has an attack. Now, with dynamic binding, late binding, it knows which one to call automatically. We don't have to do any checking. And this is just a simple. We'll have another example, even better. It calls starships because this is a starship. It calls Kling ship because this is a Kling ship. It's binding a Kling ship with that attack. It's binding a starship with that attack. If we have, however, child methods, non-overridden methods, then we have to check the type. Now picture that we have a game, we have an array that's storing these starships. The array can potentially contain any of these ones. So what type should be the array? If the type is type starship, it can actually populate with a Fed ship, because this one wants a starship, we get a Fed ship. This is where we want less, but we get more. And same with a Kling ship. And when we were playing the game, how they played the game was they had 4 different types of starships: the Federation ship, the Klingon ship, a Dominion ship, and a board ship. These 4 ships were stored in a 2D array. That was a simulated world. All these were child classes of class starship. And the 2D array was a starship, which was okay. So with a particular element now, if we're going to call one of the child methods, we need to convert, because this, say, index 0 actually is a Kling ship. But right now, it's being treated as a starship. So we have to convert it to a Kling ship. Problem, we can't guarantee at index 0 it's going to be a Kling ship, because the ships move around. It's dynamic. So before we do the conversion, we need to check, is it truly a Kling ship? And then this is almost like the envelope one. Remember the envelope? This is a starship. We package up into it. This is $100. We put an envelope that's $100. It matches up. And then when we unpackage it, call that method utter battle cry, Yes, indeed, it has that method because we're checking. Is it a cling ship? Yes, it is. Then we cast that element to a cling ship and we can do it. So how do we check the type? There's an operator called instance of, which does what you think it. Watch capitalization. Sometimes I screwed up. It checks to see, is this an instance of this class? So this is a class type. This is a reference to something. And it returns true or false. In a way, it kind of serves behavior. If you were with 231 with me, I use that type function a lot when you're trying to trace and debug programs. What we can do is to check the type of something rather than the type function. Is it true that it's an instance of? And then have debug message here. It can tell you what type of element that you have in your assignment through. If you're having problems where apparently it's calling a method inappropriately, saying it doesn't exist, then you can check in your array to see what type is that array element. Now, operations depend on type. Plus sign, what does it do? If the operands are numeric, then it's addition. If the operands are integer, it's concatenation. And not all operations are available with all types. We can't do a division on strings. Now with methods, this is behavior, actions. X, yes, we can call method 1, it's defined here. But a Y doesn't have this method. This essentially will tie into the inheritance. If we're trying to call a method of a parent object, but it's a child method. Finally, with this example, check my timeout here. There's a lot I gotta go through. So we have a parent, dead simple one. It's a simple one, but polymorphism doesn't have to be some simple text message. I'm just doing it so it's very easy to see in the trace. So class parent, overridden method, class child has an overridden method. I call it overridden so we can quickly see that this is the method overridden. This is the parent's version of it. This is the child's version, P and C. However, we have a unique, this is unique to, oops, typo here. This is unique to child, not parent, because this is the child. So you can see which method. Are we calling the parents? Are we calling the child's for overridden? Or are we calling the child method? So I've labeled it. Even though they're just simple text messages, it could be very complex code here. And even in their assignment 233, it was a fair amount of code they had to figure out. Okay. In the driver, I have a 1D array, 4 elements here. It's of type parent. But if it's of type parent, it can also contain child. We randomly populate it. This is good. I do this just so we illustrate the beauty of polymorphism. So 4 elements, each element. First, how do we randomly populate it? It's going to be 75% of the time, I'll explain 75%, a parent. 25% of the time, a child. Why? This next int, it's not in the main curriculum, but it's a useful thing for this case because I'm trying to show that polymorphism is dynamic. I don't know which element is going to be a parent child because it's going to step through each element and randomly determine if it's a parent or child. It generates a value, 1 of 100 values, from 0 to less than this. So it generates from 0 to 99. To make it easier to see, I add 1 to it. So in other words, the value that we're going to store in temp is from 1 to 100. Consequently, if it's from 1 to 100, now it's easy to see percentages. If it's between this range, 75% chance we get a parent. The other 25%, because it's the other values for 76 to 100, it's going to be a child. So it's going to be randomly populated every time. Now, if we call the overridden method, watch this, calling the overridden method. We step through the array here, index 0 to less than size, and we call overridden. And depending on whether it's a parent or child, in this case, we have 3 parents, 1 child, you can see which method it's calling. But watch this dynamically. Not only will this array be dynamically populated, oops. Okay. Now this time, oh, see, the odds, it's all parents. But we're all calling the parent, because they're all parents, calling the parent method. Ignore this for now. Populated? Oh, again, it's only probabilities. It's not guaranteed that it's going to be 3 and 1. Not a great random. Ah, there we go. Finally, you get 1, see? But we can't determine ahead of time. It's not a given, which is which. Now picture I'm randomly populating. We could have a randomly populated, like randomly generating a map. But this is a game and ships move around. So which, and I kept it simple. I made it 1D rather than 2D. But with 2D, we have a flat board. What type of ship will occupy an element? They're moving around, so it's dynamic. You don't know at a particular array element what will be what. But with this is the beauty of polymorphism. All we do is call that overridden method, and polymorphism dynamically determines whose method do we call. Beautiful. No need to check for type. Dynamic link binding, it handles it for you. That's one of the beautiful things of OO. And I hinted at it before the weekend. There it is. Easy code. However, if we have on the assignment, they also had special methods. Each one had the attack, they had their special ones of fedship, regenerate, clingship, sing. Now, if we want to call the child method, because this is an array of parents, we have to cast from a parent to a child. This is almost like taking that money, putting it into an envelope, saying, well, even though it looks like it's $10, put an envelope that's $100. Whether it's 10 or 100, we'll see when we call the method. However, before we actually do that conversion, we should, before we put it in the envelope saying it's $100, convert it to the child, we check to see, is it $100? Then we put it in an envelope. Because if we try and we don't do this check and it is a parent, then a parent, we're trying to call the child method. In earlier versions of Java, this would be a runtime error. And I think in the later few years ago, this actually, it would check it and determine it was a syntax error, prevent you from doing something stupid. So we only need to check the type if we're calling something that is unique to the child. And that's what this method is. They're all parents, so we don't call this instance of, never evaluates the true, so we never call the child method, nor should we. Again, same here. But now we have one child, array index 0 is the child. So we call that child only method. And we get, now it's array index, see, it's dynamic, 3. So I'm proving that it's able to handle it dynamically. 2. Beautiful. But the beginner's mistake is use the instance of when it's a polymorphic method. We don't need to. Now, with the arrays and objects, I implicitly did this, but explicitly, it may have seemed like it sucks in Java where it's homogeneous. It can only contain one type. But when you have references, I hinted, it's not as bad as it seems. Because a child is an instance of a parent, and if you have an array and you have different types, how can you actually have, what type should be that container? The parent. Now, if they are not, two classes are not part of the inheritance hierarchy, one isn't the parent of the other, then what you could do is have the container class object, and both of these are guaranteed to be children of class object, for instance. So it doesn't suck as much as it seems. Multiple inheritance. Multiple inheritance is here, where we've got one class having more than one parent, here and here. Dolphin is only under swimmers. Eagle is under flyers. Hawk, yeah. So these are two multiple inheritance ones. Now, this is a common behavior, say, for all of these ones. That's why it inherits here. But a duck can also swim, so it gets this behavior. Makes some sense. However, multiple inheritance. It's implemented in some old language like C++, but they made a design decision, I think rightfully, not to do it in Java. With multiple inheritance, it allows you to have that capability where you have a class that inherits from two. However, I say it requires more complex coding. What's the issue of multiple inheritance? What's the potential issue? It can be solved, but what is the issue first? Think about this one. Well, if we have a birdman object, whose flying method do we call? We have to basically resolve the scope, explicitly say which one. And it is possible, but we have to actually include that. C++, I found from experience, because it has multiple inheritance, it allows for it. When you have just single inheritance, you actually have to specifically indicate, I am calling this method, which makes single inheritance more awkward than Java. Because I think it's a good decision that they didn't make make it multiple inheritance possible because multiple inheritance is rare. By supporting multiple inheritance in C++, it made single inheritance a more common one, more awkward. That's my observation on this. But this is not just a Java class. This is OO, and this is an OO concept. That's why we're talking about it beyond just Java. And I give you advantages and disadvantages, multiple inheritance. We don't have that shared behavior here. We can't do something like this. Terminology here, single inheritance, one here, multi-level where we've got parent and then a parent of a parent or perhaps grandparent, hierarchical, two classes inherit, but it's not directly B as child of C. And then multiple inheritance we've seen terminology in case it shows up on the quiz.